Okay, Rh system. We're going to talk about the history, antigens and antibodies, inheritance, genotyping variants, and typing problems. So there's a lot to do with the Rh. Everybody knows about the ABO, everybody knows about the Rh pos and neg, but actually there's a lot more to it than just the pos and neg. So, 1939, HDN, which is hemolytic disease of the newborn, was first described. They suspected a maternal antibody, but remember, like, we really just figured out ABO in 1900s, and we really, you know, antibodies were kind of still obscure at this point. 1940, Landsteiner, right? He's the one you always have to remember, and Weiner. They were working with rhesus monkeys, and they discovered the anti-Rh. It's called that because of the Rh for rhesus monkeys. 1949, this Levine, who you'll never see the name probably again, makes a connection between HDN and the anti-Rh. So they're just calling it anti-Rh at this point. So he makes a connection. 43 to 45, they discovered the remainder of the Rh system, which isn't quite true because they're still finding Rh antigens that, you know, but the main ones that we're going to talk about. 1968, Rh immunoglobulin license. What that meant was, if we go back, 1939 was when we first figured out. It took until 1968 to actually find something that worked and licensed it. Something that's really interesting, and if you go back to probably your great-grandparents, so many of you guys are younger, my grandparents' time, a lot of times they would have like one child and then lose some or lose a lot. And if you kind of go back to it and do some family genealogy, a lot of times it had to do with this. It's kind of interesting. We actually know that this actually happened in my dad's family because of some of this. So it's kind of interesting. 1993, Tippett discovers the mode of Rh inheritance using molecular diagnostics. Remember I talked about molecular teaching us so many things as we moved along? So it took until 93 that we actually figured this out. And this is early molecular days. Something else I want to point out. This is really, really early molecular days. 2000 on through now, Rh system continues to be extensively studied because it is so serious, causes so many problems. We keep finding all these like more rare antigens out there that we didn't know existed, things like that. So we just keep studying it because it's got to do a lot with the problems we have in blood bank. So when do we Rh type? Regular transfusion practice. You all did it with your ABO-Rh typing, right? It's highly antigenic, so all donors get it, all recipients get it, all these people are always going to be typed. Prenatal testing. We do it right away when you get pregnant. You go in, you get some blood, they do your ABO and Rh in order to predict possibility of HDFN, hemolytic disease of the fetus in newborns. We want to make sure that if you are at risk, you're going to get that immunoglobulin. We'll talk a few lectures down the road about how that immunoglobulin works, because it is pretty cool how it works, but we're not going to get into that right now. So yes, so we're going to determine the need for Rh immunoglobulin. So there are 5 main antigens. Everybody knows about the D, big D. 85% of the population has big D antigen. Then you have your C's. Big C, 70% have it. Little c, 80% have it. So because of that, you can see most people have big C and little c. This is how that works. Big E, only 30% of the population has it. And little e, 98% of the population has it. Most people have little e. Now, there is no little d antigen. Little d is actually a placeholder for the lack of the D antigen. So when we get to setting these up in a little bit, we're going to do some practice problems on the board. When we get to the little d, it's just a placeholder. There is no little d antigen. You either have big D or you don't have big D. Now, big C and little c, you could have either or both. Big E, little e, either or both. But you either have big D or you don't have big D. Now, there's at least 50 others. Like I said, we keep finding them. We're not going to spend much time on any of these. little bit at the end of this lecture, we'll talk about a couple, but there's G, CW, V, VS, F. Those are like the most common ones we're going to see. If we're going to see them, but they go on and on. There's at least 50 others. Remember I told you there's over 300 groups we're going to talk, and within each group there's a lot of different antigens. This is one of those groups. So what are the characteristics that we're going to see? So remember we have this biphospholipid membrane on the outside of the red cell. Rh antigens are protein in nature. Proteins are highly complex, so therefore are going to have a higher chance of creating antibodies versus polysaccharides that are less complex in structure. So remember, developing antibodies and that sensitization, the more complex, the more likely they are to develop. So they're a protein, they're embedded in. See how this weaves in and out? They weave in and out of that cell membrane. If you have a patient with red cell membrane defects, something's wrong with your red cell membrane, you could end up with Rh no patients. They look like an Rh negative, but in reality, they have the gene to make this, and it doesn't make it because the red cell membrane is still messed up. The differences between these is usually just one protein pair different, one amino acid pair different. When you're looking for doing big C and little c, big E, little e, when we get into all the other antigens that we're going to be looking at, they're usually just one amino acid pair separates that makes it one or the other. So some characteristics of Rh antigens. Okay, the antigens. There are fewer antigen sites than ABO. Remember, on a red cell, ABO, there's over 1 million. There's fewer of these Rh antigens than ABO. They're not soluble. We are not going to find them in saliva and serous fluids. They are not expressed on tissues. These are well developed at birth. So remember, the ABO, they become more developed as the little I branches and becomes big I. When you're developing the ABO antigens, these antigens are well developed immediately at birth because they're integrated into the red cell membrane. Very immunogenic. Low dose, high probability of causing a problem. Believed to promote ammonium transport. All these antigens that we're going to talk about all do something. There's a reason they're all on the red cell. We don't know what the reasons are for all of them. But with Rh, we believe it has something to do with ammonium transport across the membrane. Now, the antibodies. Rh antibodies are formed by immune stimulus. If you remember, ABO antibodies were naturally occurring, right? They occur just because they're exposed to bacteria and things in nature. They're expected, they're naturally occurring. Rh antibodies are not. ABOs are usually going to be your IgMs. Rh's are usually going to be your IgGs. React best at 37 versus room temperature. Enzyme treatment of the red cells isn't going to enhance reactions in test tubes. Rh antibodies can cause HDFN and HTR, so hemolytic disease in the fetus and newborn and hemolytic transfusion reaction. Just make sure you know these two. You're going to see these two over and over and over. Make sure you know those two abbreviations, okay? Rh antibodies, the most common is going to be anti-D in Rh negative people. In Rh positive people, the most common we're going to see is anti-big E. Anti-big C or little c are actually less frequent because most people have both of those antigens. You guys remember how high they were, 80 and 70? So most people have both, so we don't see those as often. The reason we see that anti-big E is 30% of people have it. Only 30%. So a lot of people don't have it and are going to develop antibodies to it if they get the blood. Because 30% is enough to get exposed, but not enough where a lot of people have it. When we see anti-little e, oftentimes we see that as an autoantibody. Because 98% of the population has little e. So when we do see it though, usually it's not actually a true little e like we would think it. Usually it's an autoantibody developed against self. Oftentimes we see little c and big E together, and we see big C and little e together. So we'll see double antibodies. We'll have antibodies to both oftentimes. So here are 3 different modes of transmission, like how they're transmitted beyond to their offspring. Typic, 2 closely linked genes, D and C, C, E, E. Alleles are possible combinations of such. So they have the D is in one area and the CE is on another, but they're close to each other. These 2 are no longer, have been found not to be correct, but you kind of have to understand where they come from, because it's part of the history, and we'll go into these next few slides too. Fisher race had them as separate, 3 closely associated, inherited as a group of 3. Because remember, you usually get the whole thing inherited off, right? So you get your D, your C's, and your E's all have different loci on the chromosome. Weiner said it was all together. The alleles were all together in one loci. And they've actually found that this is what's actually correct. You have the D and the C and the E, but they're still close together on one chromosome. So here gets into the Fisher race one, 3 separate genes, 3 separate loci, closely associated but different loci on the gene, 3 separate sets of alleles and inherited as a group of 3, because very rarely do they have crossing over during meiosis. This piece is very true, okay? Meiosis doesn't tend to have a lot of crossover. The Wiener, it's 1 gene complex, and we'll get into what all these mean, like big R1, big R2, big RZ. And it is all 1, but it wasn't. So it's been more recently that we have this Tippett theory. 2 closely related genes. You get a D gene and a C and an E gene. Different combinations. So the CE is big C, little e, little c, big E, little c, little e, big C, big E. So they get passed off, they get inherited off as a group. For Rh inheritance, Rh positive people have both genes, meaning they have D and this big C, big E, little e combination. So Rh positive people have both genes. Rh negative people only have 1, because remember the little d is just a placeholder. It's not really a gene, it's not a spot. So Rh negative people only have the 1 gene. Rh is present on chromosome 1. This will get important later on in the class. Remember, ABO is on 9, Rh is on 1. When we start talking about problems in blood banking, we'll talk about that, and like where the problems come in. Oops, did I go forward too? No, only 1, okay. So why do we worry about Rh genotyping? We worry about it because we have a type of father when the mother has Rhd antibody. So if mom has developed anti-D for whatever, yeah.
I just wanted, could you repeat the one that, the antibodies that say you are Rh positive? It says what you are negative here. Just want to have it written down.
I'm sorry, what I don't understand.
What antibody is telling you that you are Rh positive?
It's gens.
Yeah.
Okay, Rh positive is D. So if you are Rh positive, you're going to have the D gene and the CE gene. If you are Rh negative, there is no D gene, you just have the CE gene. So reasons for Rh genotyping. Typing the father when the mother has anti-D to help determine how likely that baby is going to get HDN. So if mom has anti-D, she's somehow, somewhere been exposed to Rh positive blood and has developed anti-D against it. So she's D negative, she's Rh negative. She gets exposed to positive blood somehow, some way, and develops anti-D. We want to test the father. Does he have D antigen? Because we want to know the likelihood of that baby having D antigen. Because she already has antibody, that baby's going to get really sick because D's IgG is going to cross that placenta and attack those baby cells.
What if it's reversed? The dad is negative and the mom's positive?
If mom's positive, it doesn't matter. If mom has D antigen, it doesn't matter. She won't develop the antibody. There will be something we'll talk about, like K, Duffy, things like that, that mom can't have antibody for. We'll talk about those when we get to those groups. But if mom's D positive, we don't worry. We only worry about mom being D negative, because you can't make an antibody to the antigen you have. So if you have D antigen on your cells, if you're Rh positive and have D antigen, you cannot make antibody against that cell. Now there's always the caveat, right? You know, autoantibodies, autoimmune issues, things like that. But generally speaking, and I will never try tricking you on this, if mom is D positive, she can't develop anti-D. So what we want to do for genotyping is we want to see, is dad homozygous or heterozygous for D? Because when you make that Punnett square, it'll show us, do we have a 50% chance or a 100% chance that this baby's going to be Rh positive? Also, we want to use it to predict the likelihood of antibody formation in heavily transfused patients. So a lot of times what we'll do is we get these patients in, for example, sickle cell clinics. We know these people are going to get a lot of blood over the years, and because of that, a lot of times we'll antigen type and genotype them to see, how careful do we have to be to match their blood up. So this slide, print this out, write it out on a piece of paper, put it on a Post-it note. All your homework is pretty much going back to this slide, moving forward, okay? So, we look at Fisher, Race, and Weiner. We still use the terms Fisher, Race, and Weiner because even though they're not transmitted that way, they're not inherited that way, there are ways to break it down. Big D, big C, little e in the Weiner system is called big R1, and we'll get into some ways to remember this as we move forward. 42% of the population have this on one of their chromosomes. Little d, little c, little e is little r. This is our most common Rh negative. Little d is going to be Rh negatives, right? Big D's are positive. Little r, 37% of the population of the genes are going to be that. One of the two chromosomes, okay, not both, because we know that's only going to be about 15%. About 15% of the population has little DCE, little DCE on their chromosomes. So these are individual chromosomes, one or the other. Yeah.
So you don't have both big C and little c, or big D and little d?
Correct.
One of the
Each
other.
chromosome has
Okay.
a D or a non-D, a D or nothing, a big C or a little c, and a big E or a little e. And these are the different ways that they're going to show up on that chromosome.
I know you said little d is just a placeholder to tell you that d isn't there. Is it the same for the little c and little e?
No.
Okay.
They actually exist.
Okay.
Good question. C's and E's exist. Little d doesn't. There is no little d.
So the minor column is the phenotype?
Nope, it's telling us the genotype.
Then what?
It's just shorthand. So so when we look at panels, you'll see this going forward, it'll have like big R1. I know big R1 is big D, big C, little e. I just know because you have to understand how to go back and forth between them.
Okay, and then to say the phenotype, it would just be like you just described what antigen you have.
Correct.
Okay.
And when we get to the examples, we'll show you more of that though. So hang on, if I don't answer that question shortly, come back to it.
I'm sorry. Earlier when you were talking about the three different theories between Fisher, Race, Weiner, and Tippett or Weiner, it was Tippett was the guy who ended up kind of figuring
The right theory.
but
yes.
we still
use their nomenclature.
their nomenclature.
Their nomenclature.
Even though their theories are incorrect,
Yeah.
use their nomenclature that works with Tippett's.
Exactly. This nomenclature works great with Tippett's theory of inheritance.
So just to understand, so the Weedle is just shorthand for the possible combinations.
The Weiner is shorthand for the Fisher Race combination, yes.
Okay.
Does little d automatically mean Rh negative? Because there's no
On the one chromosome.
Oh, okay.
So what happens in this is you could have these two chromosomes together. And if you have these two together, they're going to look Rh positive because one of the chromosomes has a D and one doesn't.
So that's why we test for the OH to know the exact genotype?
No, that's gonna tell us phenotype. Rh only tells us phenotype. It tells us, do they have at
So
least
I'm sorry.
one big D antigen?
We test for this to know the genotype.
Yes.
That's what I meant.
What we're doing in lab this week is we'll be testing for big C, little c, big E, and little e, and then we're going to use that and use this probability to come up with your genotypes.
So as long as there's a little d, it's gonna be Rh negative if those are also or homozygous.
If it's homozygous for the little d, Rh negative.
It doesn't matter if it's big C or.
Correct. Yep, when we talk Rh positive, negative, we're only talking D. These are
But
great
if you
questions.
have one with big D and one with little d, then it's positive because you have one dominant.
Exactly. Yep, if you have any big Ds, they'll be positive.
Oh, because you have 2 chromosomes.
Yes,
of these.
this is
Okay.
one chromosome.
Okay.
Any one of these is one chromosome. So if you have any one of your chromosomes has big D,
Okay.
you are Rh positive.
And both chromosomes are the DCE combinations?
Yes.
Okay, okay.
Yeah. And remember, there's 2 different spots on the chromosome. One has D or doesn't have D, and then one has the C's and the E's.
Okay.
But because they're so close, very seldom is there crossover during meiosis, and they're usually inherited in groups.
Okay.
Okay. So a few differences, and if we go back to this slide, you're gonna see like this R naught is still pretty up there. Really, these are the 3 that you kind of really have to know quickly because they're so much higher. Beyond that, most of the time we're gonna have this. We'll talk about what the ones you need to know and why coming up. R naught is big D, little c, little e, and in the black population, you're looking at 44% of people versus white population, you're only looking at 4. So when you see this when you are getting to that probability point, and we'll talk about that when we get to probability, you have to look at your patient population. One of the things that's going to be really interesting another 10 years from now, 15 years from now, with multiracial people moving around the world, it used to be really easy. This little group had these genes. This little group had these genes. Depending on where you were in the world, like those pictures of ABO I could show you, they kind of stuck, O's mated with O's and had more O's, right? Now people are moving all over the place. People are marrying across the world. People are, it's just we're a lot smaller world than we used to be. And because of that, we're kind of seeing some of this shift over time. And we have the issue is how do we necessarily know what people identify as? I never like to assume, right? Because there's so many different combinations and backgrounds, and I like learning about people from them, but I'm never going to say, oh, that person is this background. I'm not going to say that. So it'll be interesting as time goes on. But if you look at the computers at hospitals, there's usually a place where they are self-described. Could potentially not be that. Depends on, when we get to it, we'll talk about a bit more. But when we're doing yourselves, if you, well, I should say actually by looking, if you consider yourself black, when we do your probabilities, you're more likely to have this than the other, which would be little d, little c, little e. We'll talk about that. R1, big D, big C, little e, only 17% in the black population versus 42% in the white population. So this is, R1 is the most common Caucasian genotype of Rh. So typical Rh genotypes, now we're talking with both genes, big R1, little r, big D, big C, little e, little d, little c, little e. So I look at that and I know it means that. This is the most common in Caucasians. Little r is going to be little DCE, little DCE, typical Rh negative. So you see that we have one shorthand for each of the groups of 3. R1, R2, all 5 antigens present. That's actually not too uncommon. This is the most common in Caucasians. This is going to be one of the very common in Caucasians also. But you can see this person has big C, little e, and big E. R1 lacks little c and big E. R2 lacks big C and little e. and then R naught, big D, little e, big D, little c, little e. That's very common in African Americans. So, how do we do this? We know how to do the D, right? We have our anti-D. We also have anti-big C, anti-little c, I'm missing that bottom of this picture, anti-big E, and anti-little e to determine what antigens we have. In lab this week, this is what you guys are going to be doing. You already did D last week, so everybody should know what their RhD is from last week. So you'll just write that one down. And then you're going to work on these guys. So what we do, before we get into the next thing, we take, just like we put D in a tube with anti-D, we're going to do the same thing with big C, big E, and little c. Now the difference is we are going to have to run controls for these guys. Every day that we use our regular reagents racks, they're all going to be, controls are already going to be done. You guys aren't ready to run controls for the racks until like the end of the semester. So we can't do it just yet. But when we are Rh phenotyping, you will always run controls. So what we do is we look at these anagrams. And tomorrow, because you guys aren't there yet, you'll be there in a few more weeks. But tomorrow, I'm going to have written on the board your controls for each of these, which controls you're going to use. So whether you're going for like big E, I'm going to say for positive control, you're going to use this cell. For negative control, you're going to use this cell. And you can use your screening cells. And then eventually we get these big panels out and use panel cells. Tomorrow I will find screen cells for you to use. So you'll use your 1, 2, and 3. You'll have that Roman numeral 1, 2, and 3 in your rack. Those are going to be your controls tomorrow. You also have to run one patient control because tomorrow you're not going to do the D. So remember the patient control is the anti-D against the gamma, the patient cells against the gamma clone, the control, because we want to make sure it's not reacting to anything else in that tube, right? So one tomorrow you're going to have to run a control on, a patient control, but only one. The rest of them you can just run with just a positive control and a negative control. We'll talk about it in a few minutes. I'll have the pictures up on the board. So, Rh genotyping. Tomorrow, you're going to get something that looks like this for yourself. We're going to test you. We're going to put in a tube your anti-D, which you've already done from last week, so you know that result. You're going to put big C, big E, and little e. Now, because we're doing these in tubes, they're going to have pluses and zeros. That's okay. What you're going to have to do from this point then is take this, put it in a Fisher race format, and then translate it to your liner. Okay. So, how do we do that? First thing we're going to do is start with D. One thing I want you to note, little c, put a line over. Because when you're typing, is that really a little c or did your handwriting get slow? So you always put a line over a little c to show me it's a little c. So in this case, our D was positive, C was positive. If we look this way. Little c was positive, big E was negative, little e was positive. So, we're going to start with D. If D is negative, super easy. Little d in both spots. Okay? Because we know there's no big D. However, if D is positive, all we know is at least one chromosome has big D. So you put big D there, but you're going to leave the other chromosome blank for now. So we're to there. Now we're going to look at C. Okay? If C is negative, if big C is negative, we know, boom, easy. Little c in each spot, we're good to go. If big C is positive, then we have to look at the little c result to see, are they both big C's or are they split? In this situation, our big C is positive and our little c is positive. So I know that one of these chromosomes has a big C and one has a little c, and I have to make the determination which has which. So, in this situation, it's heterozygous for C, because we have both alleles, heterozygous. So now what I'm going to do if heterozygous, whoops, finish all my words there. If heterozygous, I'm always going to put big C next to big D. So I know if I have a big D, it's going to be a big C. We still don't know if this is big or little, but we know this is where we're going to put our little c because we had the big D here. Okay? So I got my little c there because my little c was positive. So now we're going to bump to the E's. Now, big E is negative. So I look, my little e is positive. Since big E is negative, I know that I'm going to put little e's in both of these because there is no big E to put on my chromosome.
Sorry, I'm just scratching my wrist.
Oh, okay. That's okay. I'm trying to sound like, do you have a question?
No.
Yeah. Which one?
Just the E.
The E's? So because big E is negative, there is no big E anywhere on that. And because of that, I know they both have to be little e. Okay?
How did you figure out one was little c though?
Because I have a big C and a little c, and big C likes to hang with big D. I have a story in a little bit that'll help you remember that.
But you said if it was heterozygous, where did you see that heterozygous?
See how it's heterozygous? When we tested with big C and little c, with antisera for anti-big C and anti-little c, they're both positive. That's heterozygous. This one, it's homozygous for little e because big E was negative. So in the pairs, when you look at the pairs, you can tell are they homozygous or heterozygous?
So if little c was negative, then it would both be big C automatically.
Yes.
Okay.
Yeah, if one of them's negative, both chromosomes have to have the other
So
one.
both positive, then the big C will be with the big D.
Yes.
Okay.
Yep. So now, so there shows if it was both big E, they both be big E, right? If you have a heterozygous, I gotta think of how to say this. Give me a minute. If heterozygous, we can put the big E on the same one with big D if big C is not there. Okay? Let me tell you the story about the middle school lunchroom. Okay? You got your queen bee, right? First off, middle school stinks. I think we all can agree to that, right? You got your queen bee, right? She's the most popular, the most everything. She and big C, big D and big C, they're like the queens. They're the powerhouses. They're up there. They're going to make fun of everybody, including big E. So they sit at their own high school or middle school cafeteria table. Big E never sits with them. However, if big C is homesick and just little C's hanging out, big E is not good enough to hang out with this person. But only when C's sick. When C's there, the two of them are going to shun big E. Make sense? Okay. So, C and E, mortal enemies. You'll never find them together.
Unless they have to be.
Unless they have to be. Exactly, which is the next slide. Unless there's only big C's at both tables, in which case it has to be. But if they have to be, it's like teacher assignments. You know how teachers sometimes assign people who don't get along to sit together and work? That's the situation. They're only together if they're forced to be together. Okay? So now, we still have a spot to figure out. Man, what am I going to do here? How are we going to guess? We're going to go back to that slide I told you to print out or write out, however you want to do it. And I have my little Post-it notes that I study off of because I struggle to remember all of these too. Once I do them a few times, they come back. So we know, based on that little Post-it note from that slide I told you to print out, looking the wrong way. Big D, little c, little e is only 4% of the Caucasian population, while little d, little c, little e is 37. So we figured this out based on probability more than anything. Now there are molecular methods and things out there now, but not routinely used for things like this. So based on here it is. Based on probability, I know 37% is bigger than 4% in Caucasians. So I know this is going to be a little d. Okay? Now, if I look at the history and this person is a person of color, black population, it's actually more likely to be big D. But I always assume Caucasian unless I tell you otherwise. This is where it goes for you to know your population of where you're working, right? Certain parts of the country, you're going to be working at populations where 98% of your population might be black or might be Latino.
So if the person in the question is Caucasian, you're fine for little d. If the person in the question is African American, you want big D.
Yes.
Okay.
Based on, because it's a probability.
Mm-hmm.
It's like we're going to Vegas and playing the odds. Okay?
Why does 4% and 37% not equal 100?
Because remember, there's two sets of chromosomes. So if we go all the way back, yeah, look, that one. These are the probabilities of one or the other chromosome. And they're not going to total up to, like, I mean, do these total up to be 100? Actually, it's pretty close to 100. So, probability of any one chromosome.
But it can't be anything other than big D or little d.
Correct.
And there's no, as long as we know that big D is there, that's how it's going to be expressed. There's going to be no negative consequence from guessing the second D.
Correct.
Are we always probably going to have access to something that says the probabilities if we do those problems then?
On your homework, you're always going to have this. If it's a quiz, you need to know your first, primarily your first three.
The 42, 37, 14%, just
Yeah.
because they are so much higher than
Yeah.
everything else. But otherwise, will be, I guess, hints?
Yes.
Okay.
I would not expect anybody to remember like RZ, for example. Well, RZ is not too bad, but like those ones that are less than 1%, we're not going to see them very often.
If I don't know if you've explained this, if you have big E and little e, will the big E hang out with the first one, or is it?
Only if C's not there. So if I had big E, so let's flip these. Let's say big E was positive. It would be this guy. So then we'd have to look back at this. So this would be E. And then we have to look at our chart, go down that chart. Where's the first little c big E is big D. Because this is now 14%. DCE is less than 1. So it comes to probability, what we call that.
Can you go over homozygous and heterozygous again?
So homozygous is both chromosomes have the same. So homozygous, both chromosomes have big C.
So they would be both big C, it would just be, okay.
So like in this situation where this was negative,
That would be heterozygous.
this is homozygous. These are heterozygous. Because they have a different one on each chromosome. Hetero is different. These only have the little e on both chromosomes, so it's the same. That's homo same. Yes.
If the little c or the little e was negative, would you automatically then have two big C's or two big E's?
Yes.
Okay.
Yeah, if
But not
anything's
with-
negative, they would both all be positive.
The E is the only one that doesn't.
Correct. D is the only one that makes a difference there. Okay.
If you say that big E won't hang out with big C and big D, but both C's are small, little C's,
Yep.
then is it just chance which one the big E lands on there?
No, big E, yes.
Okay.
Yes.
Because like if
But
it's
if it's little, no, actually, it's not just chance. Because think, if it's little c and big D, if big C's gone for the day and little C's there, big E will step in.
okay.
Big E is like second rate.
Okay.
And big D, we know big D will never want to sit alone, right?
So E wants
Big D doesn't want to sit alone, so big D wants one of the other big ones to sit with it. Big C primarily, but not C and E together. We're gonna do several practices. I
Okay.
think that's gonna help. Okay, find my card. There it is. Okay, so this is the one we just did. That was the answer, yes.
Sorry, one more question.
Yeah.
Just because the chart only has stuff for Caucasian people, do you want us to remember that big D, little C?
Yes, remember that or not, because that will be a question, like in the question it might say an African-American man comes in, to the ER needing blood trans, it might be something like that. So if you're thinking African-American blood population, they are not.
Is
It's
that the
definitely a
only one
possibility.
that's extremely different?
Yes,
Those two are just flipped. Okay.
yeah. Okay, okay. Oh, shoot. I erased this too early. Okay, now we have to translate this from Fisher race, this is our Fisher race, to our Weiner. Big D always refers to big R. Little d always refers to little r. First thing we're gonna look at. So I'm gonna look at this. I've got a big D, I know I'm gonna have a big R. I've got a little d, I know I'm gonna have a little r. So that's the first step. Look at your D's. Big C on the same chromosome as big D is a 1. Or big C on the same chromosome as a little d is a single hash. Big E on the same chromosome as big D is a 2. Big E on the same chromosome as little d is 2 hashes. So what we're going to do is when we look at this, pretty much when you're thinking of it, I know it's a big R because of the D. The first spot to the right, if you're doing DCE, make sure they're in this order. The first spot to the right gets a 1. If I was looking at DCE, I know it's a big R, and I'm at the second spot to the right, and I get a 2. Okay. This guy has no big big C's and big E's, so he just stays little r. So this Fisher race is R1R. That means one gene is an R1, one gene is a little r, and I know by looking at these exactly what they go back to. If I had DCE, it's little r with 1 prime because the first spot to the right is big. If I've got little d, little c, big E, it's little r double prime because the second spot is big. Then there's the crazy little weird ones that are Z's and there's a Z and a Y, but those are so rare we're not going to worry about those right now. Okay, so when you're converting the Fisher race to Weiner, that's what you're going to look at. The R, little r, the big R is at the first spot or the second spot that has a big number. Or a big letter, sorry. Okay? Yes?
So how would you write the second one, the one that has R1? Is that just the R?
Big R1
Yeah.
or R prime?
R prime, yeah.
How
how do you write that? Like the one, I guess.
That's just the one prime. Little r's get primes on the top.
Yeah.
Big r's get numbers on the bottom.
So what is like the final answer then?
Well, this final answer is this.
Yes.
So if either one of them had this, it would be the R1 prime. If you had this together with this together, it'd be R prime, single prime, R double prime.
They just do it like that.
Yeah. Yeah, if it was these two together, these two genes, that's what you're looking at. Okay?
You do a comma in between, or did you?
I stick it there, you don't have to.
Might look like.
It might look like a prime somewhere, you're right. Then the other one to remember is that D with big D with no big C or big E is R naught in the black population. That's the other one you need to know. And then this is what that one is. Big D with no C or E. Okay. We already pull out, you need some scrap paper. I've got scrap paper. Here, let's go ahead and take one of these and pass them back, and then whatever's left in the back, I'll take. Yes.
So what if you were to have, if he wasn't present, but you would have a heterozygous C?
You have to have at least one E and at least one C.
Yeah,
So if big E's not positive, what?
if D is lowercase.
Oh, D is lowercase.
Yes, and what would you do with C if it was heterozygous?
It doesn't matter.
Anyway,
If no big D's there,
oh,
it can go anywhere.
Yeah, I guess that makes sense.
Yeah. I had to think through what you were asking. I'm sorry. I'm like, sometimes you guys ever notice that sometimes you ask a question, you can see my brain like doing these like tipsy turvies, like, okay, wait, what exactly are they asking and how do I explain it? So it takes a minute sometimes. Okay, so now, please actually do these with me and don't just go ahead on your notes because that's not going to help you to think through. So we have big D is 0. Big C is 0, little c is plus, big E is 0, little e is plus. So now, figure out Fisher race and the Wiener. I'm going to give you just like 2 minutes to think it through, and then we'll go through it all as a group. No harm, no foul trying on this, right? Because it's just on scrap paper and no one has to know if you get it right or wrong. Okay, let's think about it. I also want to point out, when we talk about phenotype, that's what this is. We're phenotyping it with the antisera. Right on genotype, the Fisher race and the Wiener are going to be the genotypes. They're going to tell us exactly which is on which chromosome. So, D is negative. Super easy. Starts out with little d then as a placeholder on each one. Super easy, right? Big C is negative. Little c is positive. Well, there's no big C, right? So they both have to be little c. Big E is negative. Little e is positive. So again, they both have to be little e. So that's my Fisher race. So now converting it to Wiener. little r, right? So I've got little r and little r. What about any primes? Do I do any primes with this guy? No, because there's nothing big, right? If a big C was big, it would be 1 prime. If a big E was big, it'd be 2 primes. But it isn't. So our final liner is little r, little r. Okay? Any questions on that one? We got a lot of them to go over together. We got a few here, and then we'll do some. Oh, is that really right? Okay, let's take a break.